Lab 5, Faraday's Law. Introduction. So the purpose of this lab was to observe and model the interaction of a bar magnet falling through an aluminum foil roll using our understanding of Faraday's Law. And the goals of this lab was to calculate the average time it takes for the magnets to fall through the roll and then to create a computational model to help us visualize this that ends up applying a graph of velocity versus time. The results that I got was for the observed average falling time was 1.29 seconds, and then the one I calculated from the model was 2.469 seconds. So the fundamental principles of this lab is, of course, Faraday's law, Newton's second law, Newton's third law, the Biot-Savart law of a magnetic dipole, and Lenz's law. Continued. So as the magnet is falling through the tube, it is inducing a current in rings/loops. This is where then Lenz's law comes into play, as stated in the previous slide, where the magnetic field of this from this induced current opposes the change in flux, which is pointing downwards. Faraday's law here states that the EMF is equal to the opposite direction of the change in flux, therefore it is pointing upwards. From this current and magnetic field, a magnetic force is created that acts in the opposite direction of the gravitational force that essentially slows the magnet down. And here is a little kind of diagram of the directions of the current and the flux in the magnetic field. The procedure of this law was to record a video and time a bar magnet as it's falling through the roll, and then repeat this 5 times, then calculate the average time, and then complete the closed script code, which creates the computational model. So the data as this time is as shown. The average that I got was 1.29 seconds. Here's my code. So the first part is just a bunch of constants, and the next creates the bar magnet, and this creates the magnetic field of the bar magnet. And this one is for to calculate the magnetic flux. And then over here is what computes a typical magnetic field of each ring. And then the last part, it's calculating the net force of which is just F grav plus F magnetic. And then this calculates it updates the magnet's velocity and position using Newton's second law. And here is the before and then the after of the experiment. So this is the plot that I got using a dipole moment of 2.977, which is what I calculated in lab 3. Ended up getting a time of 2.469, and then I tested it out with a different dipole moment, which was lower, to get a more closer time to what I got from when I observed, and this is what that looks like. So to interpret this simulation, because the magnet is falling downwards, the induced current is flowing in the counterclockwise direction, which opposes the change in flux, and the change in flux is increasing in downward direction. Therefore, the counterclockwise direction is shown by the blue and the clockwise is shown by the red. In this setup, the North Pole is entering first, so if we flip the directions, then the induced current will flow in the clockwise direction at the bottom, and on the bottom, and the counterclockwise will flip to the top. So the computational model was more than double than what I ended up observing, and this could be made more accurate by lowering the dipole moment, as I showed before, or by adding more rings to the tube in the observed model. Uh, so the velocity when first dropped, it quickly sped up down here, and then it slows down a bit because the tube's magnetic field is acting on it, and then the velocity reaches a plateau, which is right here, because the sum of the net force comes to 0, which is where the magnetic and the gravitational force are pointing in opposite directions, which end up summing up to 0, and then eventually it hits the ground at 2.469 seconds down here. Follow-up questions. If the conductor was reduced to as close to 0, the velocity of the falling magnet would be slower because the induced current would be larger, which can be determined from Ohm's law. And if there was holes or slots in the tube, this would affect the ring currents of the model by decreasing the magnetic field and induced current, which causes the magnet to fall at a faster time.